This is a total production. All right, everyone. So we are now looking at our spectroscopy practice focused on mass spec. So for mass spec, there's a couple of different things we can do. Technically, there's something called we could look at the fragmentation pattern, but we're not going to do that for this class. Really, what I want you to kind of get a feel for is what are three specific elements that we can identify other than carbon and hydrogen in these spectra, and then also what are some ways that we can use the parent peak that I've identified here. Okay, all of these have the parent peak identified. All right, so in looking at this first one, so the first two or three ask us to identify which element is present based off the following MS spectra. And so it really just wants an element, and it wants something other than carbon and hydrogen. All right, so what element other than carbon and hydrogen is present? Well, these two peaks right here, the parent peak and then the parent plus 2 peak, those can actually help us because there's two elements. It's either bromine or chlorine that would give us these prominent M and M plus 2 peaks. So the actual relationship in terms of the height of these two peaks will tell us if it's bromine or if it's chlorine. So for this, you notice how these two peaks are about the same height. So that right there tells us that it's bromine. Okay. Now, what is it going to look like if it's chlorine? Well, lo and behold, that is exactly what we see in the next one. It has an M and an M plus 2 peak. And you notice here, your M plus peak and then your M2. This peak is roughly 3 times the height of the M plus 2, right? And I mean, we could try to be a little careful with measuring it, but it was at 1, so it's 1, 2, 3. So yeah, so it's about 3 times the height. And so anytime you see this 3-to-1 ratio, that tells you that it's chlorine. So the first one had bromine, right, with the M and M plus 2. The second one had chlorine, all right, with the M and M plus 2 and their differing heights. Okay, now from there, in terms of identifying elements, there is one additional M plus peak that is of concern for us. So that would be looking at this example right here. This one shows us our M plus peak. If we look very carefully, the M plus peak here, see 90, 91, 92, 93. So this is equal to a mass to charge ratio of 93. What is distinctive about that? It's an odd number. Almost any other time, you're going to be seeing even numbers. Okay, so only one element is technically going to give us this odd number peak, and that would be odd number. That means it has to be nitrogen, and specifically that tells us that there are an odd number of nitrogens. Okay, all right, so those are kind of the three most easily identifiable in terms of what element is present. So the next two practice problems, they actually look at, what if I have to identify the molecule? Well, if you're given a list, say here we have these 4 molecules, right? How can I identify what this is? Technically, there is a way you can do this by looking at the fragment pattern. So like if you actually were to look at like this peak and 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 actually kind of identify like the differences in mass, you can begin to kind of isolate which one is most likely it. But the truth is, if you have a list of choices and all of them have a different mass, then you can easily determine it only based off the M plus peak. So in this case, this peak has a mass, let's see, here's 80, 81, 82, 83, 84. All right. So what I need to do is I need to look at each one of these and calculate their total mass. All right. Now, what does that mean? Well, these are nothing but carbons and hydrogens, right? So the mass for carbon I'm going to use is 12. I have to use a whole number, right? And that's the most abundant isotope of carbon. And then for hydrogen, I'm going to use the whole number 1 when I go to calculate these masses. So what do I have here? I've got, for this one, it's C6H. It's 2 hydrogens per carbon, so 12. All right, this one is C5H10. This one is C1, 2, 3, 4, 5, 6. This is C6. And that would be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. H14. And this would be C4, H3, 4, 5, 6, 7, 8, 9, 10. H10. Okay. So based off that, I'm just going to do 12 times 6 plus 12. 12 times 5 plus 10. I'm going to figure out the total masses of these. So I'm actually going to cheat. I'm going to use a calculator because I'm lazy. Alright, so here we go. I've got 12 times 6 plus 12. Oh, look, that's 84. Well, that has fewer carbons than hydrogen, so we know it's less than 84, but we'll do it anyway. I didn't mean for it to be over so soon. 12 times 5 plus 10, that gives us 70. So that equals 70. So that's not it. That's too small, right? Because our parent peak is at 84. C6H14. Let's see, what do we get here? C6H14. So that's 6 times 12 plus 14. That's 86. Right? That's too big. Nope. So, yep. And, well, that's going to be even smaller, right? Because that's 48 plus 10. So that equals 58. That's way too small. So this must coincide specifically to cyclohexane, right? And that's all you really got to do. If we look here at this guy, let's see. What can we see? Well, first off, we have 4 options. Let's look. What is our parent peak? It is at, what is that? That's 100. 1, 2, 3, 4, 5. So that's 15, 110, 115, 120. That's 121. That's an odd number. And didn't we already say something about odd numbers? That we have to have nitrogens present? So that automatically excludes the oxygen-containing ones, the ones that don't have nitrogens. And so now what we need to do is let's figure out these two and compare their total mass. So here we have C1, 2, plus 6. So we have C8. I'm going to put N1. And then for hydrogens, we've got 3, 4, 5, 6, 7, 8, 9, 10, 11. H11. Here we have C6, 7, 8. So we have C8. We have N1. Ooh, so the number of hydrogens are definitely going to have to be different. So what do we got here? We got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. All right, so those are going to have a mass difference of, because they have the same number of carbons, same number of nitrogens, but a different number of hydrogens. So they're going to have a mass difference of about 6. So let's check that out real quick. All right, so for carbon, right, we use 12. For nitrogen, we're going to use 14. And for hydrogen, we're going to use 1. All right, you can get these numbers off the periodic table, okay? Just use the whole number value, right? Don't use the decimal point value. So we're looking at 8 times 12 plus 14 plus 11. That's 121. That's the number we're looking for. Yet again, I didn't mean for that to be so quick, but we know that this is 6 times heavier, so this would actually be 127, right? So it's too big. So that's going to be our guy. All right. Okay, so hopefully this kind of helps you in terms of trying to answer these mass spec questions relatively quickly. We can at least identify structures if we have options. Okay, you're not expected to figure out how these molecules break apart. That's a bit much. Okay, all right. Adios. See you later.